Now, I mentioned before that this pyramid shape matters. There is a reason I displayed this as a trophic pyramid versus just a simple food chain. So with a pyramid shape, what you notice is that at the bottom it's the widest, and as you go up it gets more and more narrow. That's actually indicative of the number of organisms in the environment. You know, the whole earth is covered in green, and we have a ton of insects. We have quite a lot of birds, but we have snakes, but we don't really see them that much. And when you see a hawk, it's really cool. You're like, oh, look, there's a hawk. So it's almost like these are getting more rarer. And the reason why is that there's just not enough energy. So only about 10% of the energy available at one level is actually available to the next level. So let me give you an example. Let's say this frog, the entire frog, from its eyeballs to its toenails to like every single thing in that frog, let's say it could give you 1,000 calories if you eat it. Hypothetically, it could. Well, what I'm saying is that when this snake goes to eat this frog, that snake actually will only get about 100 calories worth. Meaning that snake's got to eat a lot of frogs. You have one snake, but maybe needs to eat 10 frogs. So right there's a kind of a number disparity where you have to have a lot more frogs than you do snakes. But why? Why does this 10% rule exist? Well, one, not all the material is consumed. So think about you. When you eat, let's say, like a T-bone steak, you'll eat the meat off of it. I'm going to highly doubt you eat the bones. Or you're eating some chicken wings, you don't eat the bones. If you think about, a wild animal, like wolves eating deer, usually they peel away the skin and the fur. They don't eat that. There's calories in that, though. There's calories in those chicken bones. There's calories in that deer hair, but we just don't eat it. So that's one way we're losing some calories right there, losing some energy. Another way is that maybe you do eat it, but your body just can't digest it. You literally just poop it out. So for example, owls eat the full mouse, just eat the entire thing. But they can't actually digest the bones and the fur. And what they do is they actually puke it back up. Again, there's energy in that, but their bodies are just unable to digest those materials. With humans, if you have ever eaten corn, you probably know that you will poop out that corn the next day. And the reason why is because we cannot digest the cellulose covering to a corn kernel. So if you don't chew it, you essentially are left with, corn kernels in your poop. Again, energy in it, we just can't get to it. We can't digest it and get that energy. So because less and less energy is available one step to another, that means at the very top, this hawk only getting 10 calories, from this snake. All right, well, we got to keep going. That hawk, it needs to keep eating lots and lots of snakes. All right, well, if something eats a hawk, that means it has to eat a whole bunch of hawks, but there's not that many hawks to begin with. And so that's why we don't see food chains and trophic pyramids getting really large. There's literally just not enough organisms to go around. If something ate hawks, monster with vicious teeth, you would have to eat a whole bunch of hawks. But hawks are pretty rare, so you don't really have enough of a food source. To kind of apply this more to humans, because of this transfer of energy, we could actually support more humans if we all ate grains. Because if we eat grain, let's say there's, again, 1,000 calories in this grain or in this corn, that would mean we would get 100 calories from the corn. Yeah, we'd have to eat a whole bunch of corn, but then that's it. The corn and the energy in that corn goes directly to us. However, if you eat meat, start the same thing. We have 1,000 calories in a thing of corn. One of these cows gets 100 calories, and you get 10 calories from this original corn. So it's just a lot more economical, and we can feed a lot more people if we are more vegetarian. Plus, there's a whole bunch of issues with raising cattle and sheep and chickens and pigs. We'll talk about it a little bit in this course, but if you're a vegetarian and people give you shit all the time for being a vegetarian, I'm not. I like meat. But you can say, you know, we can actually support more humans on Earth if we all ate grains. Maybe it'll help you out, because it is scientific. Like, you can explain the whole energy transfer conundrum. Point being that no matter if you're talking about humans or some other ecosystem, the shorter the food chain, so in this case we have two trophic levels, producers and primary consumers, the more energy or the more individuals can be supported than if you have a longer food chain. In a longer food chain, when we're at the top, we're not getting as many calories, meaning we need to eat more cows, and more cows are eating more corn. Again, applies to all scenarios. So let me give you an example of a problem that you could definitely see on a review quiz or on a test. It says, consider the following, the above food chain. If there are 3,200,000 incoming calories of sunlight, how much will the snake get? Well, in this food chain, there is no sunlight. So the question is where is that sunlight? Well, the sunlight is the energy source for this corn. And we're saying sunlight is 3, 2, okay. Plants are about 10% efficient as well. Of all this sunlight coming down, they can only capture about 10% of that energy to use for photosynthesis. So 10% of 3,200,000 is actually very simple. You just get rid of one of those zeros. And that's why I really like this calculation, because all you're doing is getting rid of that last digit. Well, if corn has 320,000, a locust is going to have 10% of that, which is 32,000. And the lizard is going to have 3,200. And the snake is going to have 320. But you can see that drastic difference between the amount of energy in the original sunlight and how much actually makes its way up the food chain. Now, when you see questions like these, be very careful. Where are those calories? I will tell you the calories of something. I might tell you the calories of sun, of the corn. I could even say, oh, you have 3,200 calories in this lizard. How much was in the corn? So you'd have to back calculate and add zeros. So pay very particular attention to the question and to the word problem. So as a summary, in our food chains or trophic pyramids, we have our producers, followed by our primary consumers, secondary consumers, tertiary, and so forth. But that so forth gets but so large. There's not enough energy to sustain a large number of individuals all the way up the food chain. And that's what the trophic pyramid is representing, is that change in number of individuals. Only about 10% of that energy is moving on. Now, although decomposers are not in that food pyramid, it doesn't mean they're not there. They're just kind of on the sidelines because they're feeding, so to speak, at every trophic level.